Kinetic molecular theory. So theories help us to understand why stuff happens. Laws tell us what happens, theories tell us why. So kinetic molecular theory helps us to understand the behavior of gases. Kinetic refers to motion, molecular refers to molecules. So we're going to understand gases based on the movement of the molecules. This model works for many gases under many conditions. It doesn't work for everything. But we're just going to focus on the areas where it does work. One of the nice things about an introductory course is that we can ignore some of the trickier parts. We'll just stick to where this model works. So here's a summary of the kinetic molecular theory of gases. So the first idea is that gases are a collection of particles in constant motion. Do any of you remember Pong? It's like the original video game. I meant to find a video clip of it, but in Pong, there was this little blip, and it would just move in a straight line until it hit a wall, and then it would bounce off and keep going in a straight line, constant speed, until it hit another wall. And if you had a paddle at the bottom, you had to catch it before it fell down through the bottom. If you kept catching it, it would just go on and on forever. It never slowed down or anything. That's what gas particles are like. They're in motion, they move, and they just move until they bounce into something. Second idea, there are no attractions or repulsions between the particles. The collisions are a lot like billiard ball collisions. Now, billiard ball collisions are not perfectly elastic. There is some loss of energy when those billiard balls collide. But compare billiard balls to like lumps of clay, right? You roll a lump of clay at another lump of clay, and no matter how fast you roll it, it's just going to go, boom, right? Because the clay absorbs the force, it doesn't transfer that momentum to the other ball. You roll a billiard ball at another billiard ball, and it will hit that and send the other billiard ball moving, and there's not really a loss of energy. So that's another idea. So these particles can collide with each other, but when they do, they're not attracted to each other, and they're not repelled by each other, and they don't lose energy in those collisions. So they just bounce off of each other. Another idea is that there is a lot of space between the particles compared to the size of the particles themselves. In liquids and solids, the particles are touchingly close. There's some space between the particles, but not very much. In gases, there is a lot more space than there is stuff. The particles themselves are very small compared to the size. And then the speed of the particles increases with increasing temperature. If you heat a gas up, it causes the particles to move faster. Temperature is a measure of average kinetic energy. When you put energy into a gas, when you heat it up, what happens is the particles move faster. Their kinetic energy goes up, and we experience that as an increase in temperature. So let's look at how these ideas are consistent with properties of gases. So we know that gases are compressible. If you put a liquid in a cylinder like this with a movable piston and press down on it, you can't compress a liquid because the particles are already as close as they can get to each other. And this is why hydraulic brakes and hydraulic elevators and different hydraulic systems work, is because you can put pressure on a liquid in a tube and it doesn't compress. It will transfer that pressure to some other location, wherever the end of the tube is. In contrast, if you put a gas in a container like this and press down on the plunger, you can squeeze the gas particles together. Because there's a lot of empty space here, and by putting pressure on them, you can just make them be closer together. Does that make sense? We learned that gases take on the shape of their containers. This is different than for solids and liquids. The molecules in the gas are not interacting with each other. They're just traveling in a straight line until they run into something. So if you started out with these gas particles all down in a corner, and then they start moving, right? They're just going to move until they run into something, and they're going to bounce, and eventually, in not very long at all, they will completely fill the container. Completely full, well, they will be evenly distributed. There's an awful lot of empty space between those particles. The particles go in constant straight line motion. We know that gases have low densities compared to solids and liquids. If you took a balloon full of air and a balloon full of water, which one would weigh more? The balloon full of water, right? Because water is much more dense than air. This is another orange soda illustration. I think it's interesting. I like it. If you took 1 can of soda, 12-ounce can of soda, liquid, right? And you converted that liquid into a gas, it could fill 1,700 cans of soda. That's the difference in the density between liquids and solids. The liquids are so much more dense. And the reason is that there's an awful lot of empty space. So like this, the air in this room, right? We can't see it. I'm not really smelling it, so that's a good sign. Sometimes you can see the air over Fresno, but that's not what we're talking about. But is there anything in this room? We can't see it. But there are particles in the air. There better be, or we're all going to die real soon, because we need to breathe oxygen. There are a lot of very, very tiny molecules just zinging around this room, playing their own little game of Pong, just bouncing off of everything. We don't feel them because they're always there. It's a little bit like when you get dressed in the morning, and at first you might be aware of your socks or your jeans that are a little too tight and they're kind of digging in. But after you wear your clothes for a little bit, you don't feel them anymore. That's how it is with the gas pressure. We're just used to it.